Imagine looking up at the night sky and seeing nothing. No stars, no galaxies, no glowing nebulae, just an endless void, stretching in all directions, swallowing everything in darkness. Now imagine that this wasn't just an empty patch of space. It was the entire universe. Before the first stars ignited, before the cosmos was bathed in starlight, there was an era so dark, so silent, that if you were there you would have seen absolutely nothing. Scientists call it the cosmic dark ages, a forgotten time when the universe was a cold, quiet abyss, waiting for something to change. But what really happened in this lost age? Was it truly empty? Or was something lurking in the darkness? And how did the universe finally awaken from its eternal night? Get ready, because we're about to travel back over 13 billion years to uncover the secrets of a universe swallowed in shadow. The story of the cosmic dark ages begins with a paradox. The Big Bang, the moment that created everything, was actually the event that led to this era of complete darkness. How is that possible? It all started with an explosion, but not the kind you're thinking of. The Big Bang wasn't a burst of fire expanding into empty space. Instead, space itself expanded at an almost unimaginable speed, stretching the fabric of reality in all directions. At first, the universe was a chaotic storm of energy, so hot and so dense that atoms couldn't even form. Everything was a swirling sea of free electrons and nuclei, and in this strange glowing fog, something bizarre happened. Light existed, but it couldn't go anywhere. Photons, the particles that make up light, were trapped, endlessly bouncing between charged particles. If you had been there, you wouldn't have seen anything, just an infinite haze where light was scattered in every direction. But then, something changed. As the universe expanded, it cooled, and at around 380,000 years after the Big Bang, the fog finally began to clear. Electrons and protons combined, forming the first true atoms. With fewer free electrons, light could finally escape, its first chance to travel across space. This light is still out there today, stretched by billions of years of cosmic expansion. We know it as the cosmic microwave background, CMB, the oldest light in the universe, a relic of the moment the universe first became transparent. But here's the eerie part. After this brief moment of light, the cosmos didn't burst into brilliance. Instead, everything faded into darkness. Because even though the universe was now transparent, there was still nothing to shine. For over 100 million years, the cosmos sat in silence, empty and void, waiting for something to break the darkness. And that's where the real mystery begins. The cosmic dark ages. An era so lifeless, so still, that if you were there, you would have felt like the universe itself had stopped. No stars, no galaxies, no light, just an infinite sea of nothingness. But was it really empty? Not at all. In fact, this was one of the most crucial times in the universe's history. Because hidden within this black void, something was happening, something silent, yet incredibly powerful. Across the cosmos, tiny fluctuations in density, imperceptible ripples left behind by the Big Bang, were beginning to shape the future. These weren't just random waves of gas. They were the seeds of everything we see in the universe today. Every galaxy, every star, every planet, all of it started as these minuscule clumps of matter, floating unseen in the abyss. But here's where things get eerie. These clumps weren't made of ordinary matter, at least not entirely. You see, at this point in the universe's history, normal atoms, the kind of matter that makes up you, me, and everything around us, were outnumbered. Something else was dominating the cosmos, something invisible. We call it dark matter. Even though we still don't know exactly what dark matter is, we do know one thing: it doesn't interact with light. That means that during the cosmic dark ages, the universe was filled with something we couldn't see or detect, something shaping the future of existence while remaining completely undetectable. And as these dark matter structures grew, they became cosmic traps, pulling in the scattered gas of the early universe. Over millions of years, this invisible force was slowly collecting clouds of hydrogen, squeezing them tighter and tighter. The universe was preparing for something incredible. Because deep inside these cold, dark clouds, the first sparks of light were about to ignite. For 100 million years, the universe had been a realm of perfect darkness. No light, no warmth, just an endless sea of invisible gas drifting through a cosmic graveyard. But hidden within that darkness, something had been stirring. The force of gravity, silent, relentless, was pulling together vast clouds of hydrogen and helium, the simplest and most abundant elements in the cosmos. These clouds, slowly but surely, were collapsing in on themselves, growing denser and hotter. Then, in the heart of the densest regions, something happened that had never happened before. The first atoms, crushed by overwhelming pressure, began fusing together. And in an instant, the universe changed forever. The first stars had been born. But these weren't like the stars we see today. No, these were monsters. Scientists call them population 3 stars, and they were unlike anything that exists in the modern universe. They burned hotter, shone brighter, and were hundreds of times larger than our sun. Some of them may have been as massive as 300 times the sun's mass, giants of pure energy unleashing torrents of radiation into the once black void. And just like that, the cosmic dark ages ended. For the first time, light cut through the shadows. A cosmic dawn had begun, illuminating the universe in ways never seen before. But this new light came with consequences. The first stars weren't just beacons in the dark, they were cosmic forges, violently transforming the very fabric of the universe. Their radiation ripped through the surrounding hydrogen gas, ionizing it, stripping electrons from atoms, and changing the chemistry of space itself. This was a new era. The universe was waking up, reshaping itself, preparing for something even bigger. Because as these ancient stars lived out their short, violent lives, they were unknowingly setting the stage for the next great transformation. A transformation that would give birth to galaxies. The first stars burned like celestial titans, their brilliant light tearing through the darkness. But these ancient giants had a fatal flaw. They were too big to last. Unlike our sun, which will burn for billions of years, these early stars lived fast and died young. In just a few million years, an instant in cosmic time, their nuclear fuel ran out. And then they collapsed. But they didn't just fade away. Their deaths were some of the most violent events in the universe's history. With no way to support their immense weight, these colossal stars imploded, triggering explosions so powerful that they could outshine an entire galaxy for a brief moment. These were hypernovae, explosions so energetic that they dwarfed ordinary supernovae. They didn't just destroy the stars, they reshaped the universe itself. Because for the first time, something new was being created, heavy elements. Before these explosions, the universe contained only hydrogen and helium, the lightest, simplest elements. But inside the hearts of these dying stars, something miraculous happened. The unimaginable heat and pressure forged new elements, crafting carbon, oxygen, iron, and even gold. Everything we are made of, everything on Earth, every atom in our bodies, was first born in these ancient stellar explosions. But the biggest change wasn't just in chemistry. When these first stars died, they left behind something even more mysterious, enormous black holes. These were the seeds of galaxies. Over millions of years, the chaotic remnants of these stellar deaths, gas, dust, and newly formed elements, began to swirl around these central black holes, spiraling into vast cosmic structures. Under the relentless pull of gravity, these scattered pieces began to merge, forming the very first galaxies. The universe was no longer just a sea of isolated stars. It was becoming something far grander, far more complex. But these early galaxies were nothing like the ones we see today. They were small, chaotic, and violent, filled with massive, unstable stars and raging storms of radiation. They were cosmic battlefields, where black holes grew larger, devouring entire clusters of stars, and where powerful stellar winds reshaped their surroundings. The universe was no longer in darkness, but it was still far from stable. And in the heart of these turbulent galaxies, something even stranger was beginning to form. Something that would go on to define the entire structure of the cosmos. The first supermassive black holes. The early universe was no longer dark, but it was anything but calm. Galaxies were colliding, stars were exploding, and in the chaos, something was growing, something massive, mysterious, and hungry. Supermassive black holes. Today we know that nearly every large galaxy has a monstrous black hole at its core. Our own Milky Way harbours one called Sagittarius A, a beast with a mass 4 million times that of our Sun. But here's the mystery. These cosmic giants existed shockingly early in the universe's history. How did they grow so fast? The first black holes formed when the earliest massive stars died, collapsing under their own gravity. Normally, black holes grow slowly, feeding on nearby gas and dust. But these early black holes had a secret weapon: chaos. The infant universe was wild and unstable. Galaxies were still forming, crashing into each other in violent mergers. These collisions funneled massive amounts of matter straight into the waiting mouths of black holes, allowing them to balloon in size at an impossible rate. But that's not the strangest part. As these black holes devoured matter, they became something paradoxical, both the darkest objects in the universe and the brightest. When gas spirals into a black hole, it doesn't just fall in, it forms a superheated disk, spinning at near light speeds. Friction and gravity tear it apart, causing it to blaze with incredible energy, shining brighter than entire galaxies. These quasars became the cosmic lighthouses of the early universe, colossal beams of energy that could be seen across billions of light years. If you looked up during this time, you wouldn't just see stars, you'd see these monstrous engines of destruction outshining everything around them. And they weren't just rare. We've found quasars that existed when the universe was less than 1 billion years old. Some of them are powered by black holes billions of times the mass of the Sun, which shouldn't have been possible in such a short time. So how did they form so quickly? Some scientists believe the answer lies in direct collapse black holes. The idea that instead of forming from dying stars, some of the earliest black holes formed directly from massive clouds of gas, skipping the star phase entirely. If true, this would mean that in the very heart of the cosmic dark ages, before the first galaxies even took shape, there were already monstrous black holes lurking in the void. And these black holes didn't just shape their own galaxies, they shaped the entire universe, because as they grew larger and more powerful, they unleashed devastating winds of radiation and energy, blasting apart gas clouds, halting star formation, and reshaping the fate of galaxies themselves. The universe was evolving at a breakneck speed, and as the first galaxies stabilized, something even more incredible was about to happen, something that would bring the cosmos one step closer to what we see today. The birth of modern galaxies. The universe was no longer a featureless void. Galaxies had formed, turbulent, violent, chaotic. But they were still young, primitive, and unrecognizable compared to the grand spiral and elliptical galaxies we see today. The cosmos was in the middle of a transformation. The question was, how did these early galaxies evolve into the enormous structures that now dominate the universe? The answer: mergers. Gravity was pulling galaxies toward each other, forcing them to collide in some of the most spectacular and destructive events in cosmic history. But these weren't gentle meetings. They were cosmic train wrecks where entire star systems were torn apart, black holes devoured everything in their reach, and enormous shockwaves reshaped the very fabric of space. And yet these collisions were the key to progress. When two galaxies merged, their stars mostly passed right through each other, since the space between them was so vast. But their gas and dust, the raw materials for new stars, slammed together, compressing into dense regions that ignited waves of new star formation. These weren't just any stars. They were some of the brightest and most powerful the universe would ever produce. Over hundreds of millions of years, small galaxies merged into larger ones, feeding their central black holes and triggering bursts of star birth. These mergers continued, creating the cosmic giants we see today, galaxies like the Milky Way and Andromeda, each home to hundreds of billions of stars. But something else was happening, something that would shape the very structure of the cosmos itself. Galaxies weren't just randomly scattered. They were aligning into something much bigger, a vast cosmic web stretching across the universe. Clusters of galaxies were forming, linked together by filaments of invisible matter, and at the intersections of these filaments, the largest cosmic structures were taking shape. Superclusters, colossal regions containing thousands of galaxies bound together by gravity. But here's the mystery: what was holding them all together? Something was influencing these galaxies, shaping their motion, yet it was completely unseen. Scientists began to realize that a hidden force was at play, something that outweighed all the visible matter in the universe. This was the first hint of something that would become one of the biggest mysteries in astrophysics, a mystery that still baffles scientists today: dark matter. The universe was beginning to take shape. Galaxies were merging, stars were forming, and the first great structures were emerging. But there was a problem. Something was missing. When scientists studied these early galaxies, they noticed something strange. The stars were moving too fast, far faster than gravity alone should allow. According to the known laws of physics, these galaxies should have flown apart, their stars flung into the abyss. But they didn't. Something was holding them together, something unseen, something powerful. This was the first clue that most of the universe is hidden from us. We call it dark matter, an invisible, unknown form of matter that doesn't emit, absorb, or reflect light. We can't see it, we can't touch it, but we know it's there because of how it bends the fabric of space itself. Dark matter isn't just a cosmic curiosity, it's the very scaffolding of the universe. Imagine an enormous web of invisible threads stretching across billions of light years. These filaments of dark matter acted like a cosmic blueprint, guiding galaxies into place, shaping their formation and pulling them into clusters. Without dark matter, the universe wouldn't look anything like it does today. Galaxies wouldn't have enough gravity to stay together, stars wouldn't orbit the way they do, and the entire cosmic web, the vast interconnected network of galaxies, wouldn't exist. But here's the real mystery. We still have no idea what dark matter actually is. Scientists have spent decades trying to uncover its true nature. Some theories suggest it's made of exotic particles, WIMPs, weakly interacting massive particles, or axions, strange particles that barely interact with ordinary matter. Others believe dark matter could be linked to hidden dimensions, unknown physics beyond our understanding. And then there's an even wilder possibility. What if dark matter isn't matter at all? Some scientists speculate that it could be an illusion, an effect of modified gravity, meaning our entire understanding of physics might need to be rewritten. But whatever dark matter is, one thing is certain: it's everywhere. It surrounds us, it shapes galaxies, and it makes up 85% of all the matter in the universe. Without it, the cosmos as we know it couldn't exist. But dark matter isn't the only invisible force at work, because as galaxies were forming and merging, another force, one even stranger, was beginning to reveal itself. Something even more mysterious than dark matter. Something that wasn't holding the universe together, it was tearing it apart. Dark energy. Galaxies had formed. Clusters had taken shape. The cosmic web was stretching across the universe. Everything seemed to be settling into place. But then, scientists noticed something that shouldn't be happening. The universe wasn't just expanding, it was expanding faster than ever before. This made no sense. Gravity should have been slowing it down. Every galaxy, every star, every planet, all of it should have been gradually pulling on each other, putting the brakes on the universe's expansion. Instead, it was speeding up. Something was working against gravity, something unseen, something powerful enough to counteract the pull of all the galaxies combined. We call it dark energy. Unlike dark matter, which holds galaxies together, dark energy is doing the opposite. It's ripping the cosmos apart at an ever-increasing rate. And here's the truly terrifying part. Dark energy makes up a staggering 68% of the universe. That means everything we can see, galaxies, stars, planets, even dark matter, only accounts for a tiny fraction of existence. The rest is an invisible, unstoppable force, pushing the universe apart at an accelerating pace. But what exactly is dark energy? Right now, we have no idea. One theory suggests it's a property of space itself, vacuum energy, a strange force woven into the very fabric of the cosmos. If true, then the more space expands, the more dark energy there is, fueling the acceleration even further. Others believe it could be linked to a fifth fundamental force of nature, one we have yet to fully understand. Some have even suggested that dark energy might be connected to hidden dimensions beyond our own, leaking through from a reality we cannot perceive. But here's where things get truly mind-bending. If dark energy continues its relentless push, the universe could face a catastrophic fate billions of years from now. There are three terrifying possibilities. The big freeze dark energy keeps pushing, galaxies drift farther apart, stars burn out, and the universe becomes a cold, empty void, silent and lifeless for eternity. The big rip dark energy gets stronger over time, tearing apart galaxies, stars, planets, even atoms themselves, unraveling reality at the deepest level. The big crunch dark energy somehow reverses, gravity takes over, and the universe collapses back in on itself, potentially leading to a new Big Bang. Right now, we don't know which of these fates awaits us, But one thing is certain, dark energy is rewriting everything we thought we knew about the universe. It is the most powerful force in existence, and yet we don't know where it comes from, why it exists, or how it will shape the future of reality itself. But while we try to solve this mystery, there is one final chapter in the story of the cosmic dark ages, a chapter that reveals the oldest light in the universe, a whisper from the past, still echoing through space. The cosmic microwave background. For hundreds of millions of years, the universe was a dark and silent abyss, shrouded in a fog of hydrogen gas. No stars, no galaxies, no light, but something was waiting beneath the darkness, a relic from the beginning of time itself. A faint whisper, a ghostly glow, the oldest light in the universe. We call it the cosmic microwave background, CMB, the afterglow of the Big Bang, stretched across the universe like an ancient fossil. So what exactly is it? To understand the CMB, we have to rewind nearly 14 billion years, all the way back to the moment the universe was born. In the beginning, the universe was an unimaginably hot, dense fireball. A place where matter and light were trapped together, constantly colliding in a chaotic plasma. Photons, particles of light, couldn't travel freely. They were scattered endlessly by charged particles, making the universe completely opaque. But then, something changed. About 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. Electrons and protons combined to create neutral hydrogen, and suddenly, light was free to move. The fog lifted. And that first light, the very first photons to ever travel freely through space, became the cosmic microwave background, a snapshot of the universe in its infancy, forever imprinted onto the cosmos. For billions of years, this ancient light has traveled across the universe, stretching as space expands. Originally, it was searingly hot, glowing with the intensity of the sun. But after nearly 14 billion years of cosmic expansion, it has cooled down to just 2.7 degrees above absolute zero. A faint microwave signal spread evenly across the sky. It was everywhere, surrounding us, filling the cosmos. But for most of human history, we had no idea it existed. Then, in 1964, two radio astronomers, Arno Penzias and Robert Wilson, accidentally discovered a strange signal coming from every direction in the sky. No matter where they pointed their radio telescope, a faint, persistent noise was there. At first, they thought it was a mistake, maybe interference from their equipment. They even cleaned bird droppings off the telescope, thinking that was the cause, but the signal remained. That's when they realized they had found the oldest light in the universe. The cosmic microwave background wasn't just a discovery, it was proof. Proof that the universe had once been a hot, dense fireball. Proof that the Big Bang had really happened. Proof that we could look back in time and see the universe as it was nearly 14 billion years ago. And this ancient light wasn't just a cosmic relic, it held secrets. Subtle ripples in the CMB revealed the first patterns of structure in the universe. The seeds of galaxies and clusters that would eventually form everything we see today. This light is still traveling, still surrounding us, still whispering the story of the past. The cosmic microwave background is the final echo of the Dark Ages, the moment the universe finally stepped into the light. But the story doesn't end there. There's one last mystery to uncover, the ultimate fate of the cosmos. How does the universe end? Does it fade away into darkness, collapse back into nothingness, or continue expanding forever? We are about to explore the final chapter in the story of everything. For billions of years, the universe has been evolving, expanding and transforming. From the fiery birth of the Big Bang to the formation of galaxies, stars and planets, we exist in just one fleeting moment in cosmic history. But what happens next? How does the universe end? The answer to that question depends on a battle, a struggle between two cosmic forces that have been at odds since the beginning of time. Gravity, the force pulling everything inward, trying to slow expansion and pull the universe back together. Dark energy, the mysterious force accelerating expansion, pushing the cosmos apart at an ever-increasing rate. The outcome of this battle will decide the ultimate fate of everything. Scientists have outlined three possible endings, each one more bizarre than the last. The Big Freeze, the eternal silence. This is perhaps the most haunting scenario. If dark energy keeps pushing the universe apart, galaxies will drift further and further away from each other. Stars will eventually burn out, their fuel exhausted. Without new stars forming, the cosmos will become cold and dark. Over trillions of years, black holes will slowly consume whatever is left, until they too evaporate. The universe will be nothing but a vast, empty void, silent, frozen, and lifeless for eternity. The Big Rip, the ultimate destruction. This is the most violent and chaotic possibility. What if dark energy doesn't just keep pushing, but gets stronger over time? As the expansion speeds up, galaxies will be torn apart, then solar systems, then planets. Eventually, even atoms themselves won't be able to hold together. Space-time itself could tear apart, erasing everything in existence in a final, catastrophic event, the ultimate end of reality. The Big Crunch, a new beginning? This is the opposite of the Big Freeze. If gravity overcomes dark energy, the expansion of the universe could reverse. Galaxies would collapse inward, drawn back together. Stars and planets would smash into each other, and the universe would shrink until it becomes a searingly hot, infinitely dense point, a mirror image of the Big Bang. Would this be the end? Or would it lead to a new Big Bang, a cyclic universe that expands, collapses, and is reborn again and again? Or something else? There's also the possibility that we're missing something entirely. What if there are hidden forces at play? What if we discover new physics that changes everything we thought we knew? Could we learn to manipulate the fabric of reality itself, escaping our universe before it meets its fate? Right now, we don't have the answers. All we know is that the universe had a beginning, and one day it will have an end. But until then, we exist in the golden age of the cosmos, when stars still shine, planets still form, and life against all odds can witness the story of the universe unfold. And perhaps by understanding the cosmos, we will one day understand our place within it, the end, or just the beginning. The mysteries of the universe are endless, and there's so much more to explore. So if you enjoyed this journey through the cosmic dark ages and the fate of everything, don't forget to like, subscribe, and hit the bell icon for more deep dives into the most fascinating secrets of the cosmos. Until next time, keep looking up.